Thank you very much. I think you've probably been quite generous with the decade, and I'll show you why. So I want to say thank you to the organisers for inviting me. This is a somewhat different audience to what I'm normally used to talking to. Our group's based in Edinburgh. We're called Camarades, which stands for the Collaborative Approach to Meta-Analysis and Review of Animal Data in Experiments. In experimental studies, even. I've never actually had to say it before. So what we do is we perform systematic reviews and meta-analyses of animal experiments. If we think that preclinical studies are generally performed with the purpose of improving human health, then those experiments need to be rigorous, they need to be reproducible, and they need to be available. So what we do is use systematic review meta-analysis to assess the quality and range of animal data that exist. We use them to identify gaps in the field. We've used them to assess a publication bias. We've tried to explain the discrepancies that we've seen between the positive results that you often see in animal experiments compared to the results that you see in clinical trials. And we've also recently used them to inform how we design clinical trials. We generally perform these slightly differently to clinical systematic reviews because of some fundamental differences in the type of studies that we're looking at. For animal experiments, you generally have many small experiments in the tens animals per study, whereas for clinical trials, you may generally have fewer but much larger, hundreds or thousands of patients. But I want to stress that I'm going to show you lots of data that shows information from these different headings that I've got here, that this type of research is observational, it is looking at the studies that have already been completed, so should be considered hypothesis generating. So as I said, I'm from Scotland, and I always like to get a Scottish example in, but I have a slight American start here. So this is data from a survey that was done in the States, looking at support for the legalization of gay marriage. We see early on there was more opposition than there was support. This is the x-axis here has the years that the survey was conducted. However, in 2009, Susan Boyle, she wowed the world with I Dreamed a Dream on Britain's Got Talent, and then something happened and there seemed to be a shift in support for the legislation of gay marriage. So I'm not saying that Susan Boyle caused Americans to support gay marriage, but what I am saying is that Susan Boyle happened and then support of gay marriage happened. I think it's a nice example of correlation versus causation. And I want people to keep that in the back of their minds when I go through some of the data that I'm going to show you next. So this is just an outline of my talk. I'm going to explain what I mean by translational failure, and then give some examples of the internal validity of experiments, construct validity, and reporting biases. So we came to this research with the hypothesis that in the life sciences, and I'm talking about in academic research generally, there are perverse incentives, things like getting published, things like securing funding, things like being promoted to produce positive results with little attention paid to the validity of these results. In the use of animal disease models, they are additional pressures to reduce the number of animals that you use because of the cost, time, ethics, and feasibility, which results in lots of studies being generally underpowered or being of unknown power. And I think together these factors combine to compromise the utility of animal models and likely contribute to translational failure. I'm going to give an example from stroke research. That's where a lot of the research that I did began with. And this is a study that was done by some colleagues in Australia. They identified that, a systematic review identified that over 1,000 interventions have been studied in models of stroke. Over 600 have been tested in vivo models of stroke. 374 of these interventions appear to be effective in these stroke models. 97 were carried forward to be tested in a clinical trial. However, only one intervention, thrombolysis with TPA, was shown to be effective in a clinical trial. So we're clearly missing our target. So from stroke animal data, it's clear that they are huge amounts of data, and we're of the opinion that systematic review may be useful to try and make sense of these data. So this is an example from a review that we did a few years ago where we looked at therapeutic hypothermia in animal models of stroke. Our systematic review identified 222 experiments. We have just over 3,000 animals, and what you can see here, so these are each of these 222 experiments ranked in order of increased effect with the 95% confidence intervals, and we have the global estimate in this grey bar behind. And from the published literature, you can select extreme bits that show that hypothermia is either dangerous or it's substantially beneficial. And what we use meta-analysis for is to try and investigate the sources behind this variation to try and improve or help the process of translation. I've talked about translation from preclinical studies to clinical trials, but even within just preclinical studies, sorry, excuse me, there have been difficulties in replicating from one laboratory to another. And these are just two examples from industry where they took published academic results and then tried to replicate those studies in-house. And Bayer was able to replicate 36% of the studies that they tried to, and Amgen was only able to replicate 11% of the studies that they tried to replicate in-house. So I'm going to talk about internal validity. So this concept that the integrity of the cause-effect relationship. So are we sure that the effect that we're seeing in our outcome is due to the intervention rather than by some sort of other unknown risk of bias? This is an example from the early 60s where Rob Rosenthal, he was a psychology professor, and he decided to run an experiment with 12 psychology graduate students. And he took what is called a T-maze, where you will introduce a mouse, you reinforce the dark side, and you have a light side. And as it's a test of memory, so the mouse, you introduce it here, and the ones that remember that the reward is on the dark side should go to the dark side of the T-maze. He split his students into two groups. He told them that I have some rats and mice who have been bred for generations and generations to be really good at finding the dark arm. So these were the maze bright mice. And then he had a group of mice that he called maze dull, and these were mice that just were not very good at learning or memorizing. And what he did was gave these mice to the students, and when they ran the experiment, the students found a difference between these mice, that the maze bright mice were consistently better at finding the dark side of the arm. Of course, the test wasn't of these mice, he was testing the students. There was absolutely no difference in these mice whatsoever, and they were just randomly selected from the animal house. And when they spoke to the students afterwards and asked them about the differences in these mice, they said, oh, you know, the maze bright ones were cute, they were cuddly, the maze dull ones used to bite us, and they were angry, really stupid mice. So this shows the intrinsic bias that was amongst people who were performing the studies. Now, this example was from the early 60s, but to be honest, I don't think a huge amount has changed in how animal experiments are still performed. This is an example from a systematic review that we did looking at an intervention called NXY059. So NXY is an antioxidant. It was trialed in a large phase 3 clinical trial. More than 3,000 patients were randomized into this trial, and NXY failed to improve outcome. So what we did is we went back and looked at the animal data. Our systematic review identified 11 publications, 29 experiments, just over 400 animals, and collectively these data appear to improve outcome. We see a 44% improvement in outcome overall. However, when we stratify the data according to the studies that were randomized, that blinded the conduct of the experiment, or that blinded the assessment of outcome, we saw consistently that studies that took measures to reduce the risk of bias reported substantially smaller treatment effects. In addition to that, none of the studies reported all three measures to reduce the risk of bias. And in the trial brochure that they used to convince people to participate in the trial, the evidence that they cited that said that we've shown this drug to work in animal studies, again, didn't report any of these measures to reduce the risk of bias. But it's not just in stroke. Our work includes a review of a number of different neurological disorders. And we see across the modelling of stroke, but motor neuron disease, Alzheimer's disease, Parkinson's, EAE, which is a model of MS, and glioma. Few studies report randomization. Fewer studies report blinding the assessment of outcome. And hardly any studies report performing a sample size calculation. One of the comebacks that we often get when we present our research is that, well, you're looking at studies that aren't published in very high impact journals. They're not very well conducted studies. If you looked at studies that were published in the highest impact journals, then these would be much better quality publications. So we went and we looked at whether there was a correlation between the quality of the study that was reported and the impact factor of the journal that it was published in. So first of all, we looked at reporting of a conflict of interest. So on the x-axis here, we just have decile of impact factor, and on the y-axis we have prevalence, and these dotted lines are the 95% confidence intervals. And we see the high impact journals generally tend to report a conflict of interest statement. There's a flat line between the impact factors of the journal and whether they report sample size calculation. It's a flat line between the quality of the journal and whether they report blinding. And we actually see a negative correlation between the impact factor of the journal and whether they report randomization. So I don't want to just naysay and say everything's bad. I think it's important to come up with some sort of strategies, or at least some ideas about how we can improve what we do. I think different stakeholders have different roles to play in what we can do to improve reporting. Journals have a role. The ARRIVE guidelines, which are an animal equivalent, I guess, to CONSORT, many journals have endorsed the ARRIVE guidelines to try and improve the quality of reporting. Landis is a similar type of, it's a much shorter set of guidelines, but again, it's put together to try and encourage people who are reporting their studies to include key information that allows you to assess the rigor of the experiment. Nature changed their publication policy, but also audits and RCTs of these guidelines may help improve uptake. Funders have a role. I think emphasising rigour in the grant award process is an important thing to do, but also institutions in terms of auditing performance of scientists and also continued professional development opportunities for scientists as well. So now I'm going to talk about construct validity. The work I'm showing you is looking at modelling human diseases, but we need to be sure that what we think we're modelling in an animal represents what we think we're trying to then translate to in a human setting. That's what I'm talking about here, the generalizability. So this is an example of how the wrong model may be used. So I've spoken about NXY, so this was a failed large clinical trial, and TPA is the intervention that is routinely used to treat stroke. So these are both data from systematic reviews of the animal data, and we stratified the animals according to those that had hypertension modelled and those that didn't. Hypertension is prevalent in people with stroke, and what we see here for the NXY data is that 7% of the animal studies were hypertensive, and NXY was substantially less effective in these hypertensive animals. 77% of the patients were hypertensive. When we compare to the TPA data, still a very small proportion of the data was hypertensive for animals, only 9%. However, the clinical trial specifically excluded hypertensive patients for the trial. So in this scenario, it appears that the clinical trial was testing TPA in a scenario where efficacy had been shown in the animal studies, unlike the NXY dataset. Here we've looked at time to treatment. So for stroke, time to treatment is a very important variable. This is the TPA data again. I've got the animal data on the left and the clinical data on the right. We stratify the data in epochs of 90 minutes, and we see a very similar pattern between the drop in effect in the animal studies and the clinical trials. So you do have scenarios where you do see concordance between the clinical trial and the animal data. This is an example from a different disease model, EAE. This was a model of MS, and we looked at all the EAE literature that had been published, and we identified that nearly 50% of the data the animals were being treated for EAE before they inoculated the animals. So they treated them, and then they gave them the disease, and then they assessed outcome. Another 22% did it on the same day. Now, I'm not a neurologist, but I know that a patient needs to have symptoms and be diagnosed before they're treated. So we see a mismatch between the design of animal studies and what happens clinically. So again, I think improvement strategies are useful. I think we need to develop better validation of animal models. There are some things going on for targeted experiments, but I think systematic reviews can be useful for comparing models and outcome measures that are used. And again, I think it's important to design clinical trials to test where efficacy has been shown in preclinical studies if you're going to use the preclinical studies to justify your clinical trial. Now I'm going to quickly cover reporting biases. So a number of different reporting biases that can exist. I said we have perverse incentives in academic research, and one of the biggest issues that we have is that we have to publish. But to get published in high-impact journals, there is a tendency to support big effect sizes, big significant effects. So neutral or negative studies tend not to get published, or if they do get published, it takes much longer for that data to be disseminated. In animal experiments, there's also a tendency to assess lots of different outcomes because you can in that controlled environment. But what we have seen is that when you could assess, I don't know, 20 different outcomes, when you do your statistical test, only those that are significant tend to make it into a publication. So you get selective outcome reporting. And then you have a thing called vibration effects, which is essentially running a number of different statistical analyses on your data set and then reporting the analysis that shows to be significant. I don't know how many of you follow the hashtag overly honest methods on Twitter. It's a bit tongue-in-cheek, but it can be quite entertaining. But this is an example that makes this point that we made a thorough comparison of all post-hoc tests while our statistician wasn't looking. So in our stroke data set, we assessed for publication bias. We used 3 different techniques. First of all, a funnel plot. So what you do is you plot the effect size on the x-axis, the precision on the y-axis, which is the inverse of the standard error. And where you have no publication bias, you expect to see that the more precise the study is, it should lie around the true effect. And as you become less precise, you should have an equal distribution of both positive and negative effects. However, we see here that we have a lack of imprecise negative data in the public domain. You can statistically test for this asymmetry using egg regression, where you plot the standardized effect size against the precision, and if your funnel plot is symmetrical, your regression line and its confidence intervals should go through the origin. Here it doesn't, which again suggests that there is supportive of publication bias. The final test that we ran was a technique called trim and fill, which tries to estimate these theoretical missing studies by essentially imputing what it thinks are missing to have a much more symmetrical funnel plot. And in this data set, our overall effect was reduced from 32% down to 26%. So in experimental stroke, trim and fill suggests that 16% of experiments remain unpublished. The best estimate of the magnitude of this problem is that we're overstating our treatment effects by about 1/3. Now, I think this is a gross underestimation of the magnitude of this problem. In our data set, only 2% of the publications reported no significant treatment effects. So lots of those studies that were on the left-hand side of my funnel plot were experiments that were published in the same paper as significant studies. They weren't truly wholly negative studies. Again, we've looked at the presence and impact of publication bias in different disease models, and we see the same thing. Around 20% of studies remain unpublished, and we're overstating treatment effects by about a third. Publication bias appears to have different patterns depending on what you're looking at. So the data, all the data I've shown you today actually is looking at modeling a disease where your outcome is to improve, where you want to improve your outcome. And we see that when we try and assess for and correct publication bias, there is actually less improvement. We've also looked at toxicology studies where your outcome is in the opposite direction. And when we assess a publication bias in these studies, we see the exact opposite, that there is more harm than is being made publicly available. So, improvement strategies. I think journals, we're not the Sunday Sport, we're not the Daily Mail. I think there should be a journal of record. So if animals are going to be used for science, then the data from those animals should be made public. Some of these might be considered a little bit out there, but one solution potentially may be that funders withhold 10% of a grant until you've published your study, or maybe support new publication models that allows for publishing protocols or registries of animal studies to make sure that we know at least the experiments that have been performed if they're not published in traditional journals. And institutions, I think, need to encourage non-vanity publishing. So it's not about the highest impact. And if you're going to look at appointments and permanent appointments in institutions, it's about looking at the work rather than the impact of the journal that it was published in. So I think, how can we increase the chances of translational success? I think systematically reviewing all the data that exists is part of that process. And then if you are required to do further in vivo studies, if that's indicated, I think that's important. I think clinical trials should be designed accordingly. And I do think we need tools to allow rapid living systematic reviews, so we're always up to date on the current information that's out there. So the key messages that I want to take home is that in vivo studies which do not report simple measures to reduce the risk of bias tend to give larger estimates of treatment effects. Most in vivo studies don't report simple measures to reduce the risk of bias. Publication bias and selective outcome reporting biases are important, and they are prevalent in the preclinical literature. You can't assume rigor, even if the journal is of a high impact. I know we have editors from quite high impact journals here, so I'm saying that with trepidation. And I think these points, you can only really find them out by studying large numbers of studies, by performing these large systematic overviews of the literature. I think it's important to know that any experimental design can be subverted, but it's important that we know how to recognise when this has happened. So having the expertise to understand when a study has been conducted well or not. And with that, I want to thank you for your time.
Thank you, Emily, and I think we do have time for a few questions, and I was delighted, since I don't interact that much with lab-based or animal-based journal editors, that you had many criticisms of that, and you left out clinical editors for a change. So questions for Emily?
Kit Bryant from Hereford. I also have to declare an interest. I'm a trustee of a charity that funds alternative to animal medical research. And it strikes me that one of the big players here, one of the big influences, are the charities that raise money for disease-specific research, which is often, understandably, very emotive, and is a massive drive. The amount of money involved is massive. And I wonder whether you've done anything to engage with the charities that oversee or that fund that research to help give them a guide into good governance. Otherwise, they're wasting their donors' hard-earned money or hard-donated money.
That's a good point. No, not, well, recently have a grant in with Diabetes UK to say in their portfolio they funded lots of animal experiments, and we want to assess the rigour of that field generally. So just recently we've tried to get involved in engaging with charities, but it's a good point because it's huge amounts of money that are invested in animal experiments.
And for all the 3 R's that have been spoken about in the last decade, the number of animals that have been experimented with has risen dramatically. So something's not going right.
No, so I was having a conversation with somebody over lunch about this actually. So the 3 R's reduction, I think, is a very misunderstood R. It's not about, I personally think it's not about reducing the number of animals per se, but it's getting valuable information from the least number of animals that you need. Generally, the experiments that we've looked at are underpowered. You're looking at an N of 4, 5, 6. That's not sufficient data to get a reliable answer. So you may need to, I would argue, fund fewer studies, but larger. So you may need more animals to get the right answer.
Other questions? Right behind.
Ian Chalmers, Oxford. Just to comment on this, a few years ago I was asked to chair the Research Development Committee for the Multiple Sclerosis Society. And I accepted on a number of conditions, one of which was that before any proposal for new research was agreed for funding, systematic reviews of what was already known should be done. It was a bit I put all of these conditions in advance of my first meeting, and it was quite disappointing at my first meeting when a very, very senior physiologist member of the committee said that this was outrageous demand and he was now resigning. Now, in fact, Emily's colleague, Malcolm MacLeod, at my suggestion, came and spoke to the committee subsequently, since when it has become, in fact, the policy of the Multiple Sclerosis Society to insist on systematic reviews, both of animal studies and of clinical studies, before they consider funding new studies, which is consistent with the initiative taken by Hans Lund, who's at this meeting, and his colleagues, called evidence-based research. In other words, you should find out what's known already before you embark on new studies.
Thank you for the comment. Ian, one other question?
Just a quick one. I really did enjoy that enormously. Looking back on my animal experimental days, we used outbred animals, and of course all the problems that you mentioned would arise. But over the last 20 years, most the critical experiments are done in genetically identical, inbred strains of mice, for example. How do you estimate the power that you need? Because there again, you're talking about N equals between 5 and 10, but these are genetically identical, where the only difference is the intervention. It doesn't get rid of course, the cognitive bias of the investigators, but...
Well, it depends on the size of the effect that you're looking at. You're right, generally, mice now, or even rats, are inbred. That's what's used, which I think is part of the problem with replication. Because if you show an effect in your lab in that inbred strain, for somebody else to replicate the same effect in their lab in another inbred strain has been a problem. So we've been pushing recently for designing essentially what will be a phase 3 preclinical trial. So international, different centres involved, the step, almost like the step before you would go into a clinical trial, to show that you can show an effect outside of your own laboratory. Because I think one of the problems with inbred strains is generalizability. You do just repeat, you can show your effect in your lab, but nowhere else.
Thank you, Emily.
Thanks.
Excellent.